Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we're very happy to have Noga here. He was a frequent visitor in the past, had a break of a few years, but we hope he'll resume the frequent visits from now on. And he'll be telling us about eliminating cycles in the torus.
Okay, thanks. Right, so I promised to eliminate cycles in the torus, and I'm going to do it on the whiteboard. So we'll have, maybe I'll write the title, Cycles. Torus. And I want to first define the torus, actually the tori I will be speaking about, because there will be three of them. Incidentally, please do not hesitate to stop me whenever something doesn't make sense. So you are okay. So we'll have definitions. Two of the tori will be discrete. It will be graphs, and one of them will be the usual continuous torus. So these are definitions or notations. CMD1. So that's a notation for one graph. So that's a graph. The vertices will be Zm to the d, so sequences of length d of elements of the group modulo of integers modulo m. And I have to define when two are adjacent. So x1 up to xd is adjacent to y1 up to yd. These are two typical vertices, if and only if. So let's write it like this. So the sum of xi minus yi mod m, and we take the absolute value, and we write here 1. And what this means is that the two vertices, or the two vectors, sequences, are equal in all coordinates, and in one coordinate, they are consecutive modulo m. Right? So they are. So for d equals 2, this is the picture is this, and it's a torus. So as usual, we identify top and bottom and left and right. So this is this graph. Didn't get it?
Can I do Lalas into a false sense of security?
Yeah. Okay. I agree. Okay. So this is one. Then we'll have a similar graph of a torus. So this will be CMD infinity. So that's also a graph. And the vertices are the same, CMD. And now two are adjacent, if and only if, and we take the L infinity norm. So that will be the maximum over I between 1 and d of the same thing, xi minus yi mod m, like this, equals 1. And maybe I'll make it smaller. So to be adjacent in each coordinate, they have to be either equal or adjacent. And again, it's in the torus, and this is a picture. So it's another graph. Okay? And then we have the continuous torus. So this will be a T, D. This will be so if you want, it's RD modulo ZD, but it's just the continuous torus. And the picture for dimension 2 is this. Okay. So these are three tori, and we want to ask something about them, and afterwards I'll tell you why we are doing it. So these are problems that have been considered before. So I want to define what is a non-trivial cycle in each of these tori. So a cycle is non-trivial if it is not homotopic to a point, but I'll just write informally if it wraps around. Namely, we cannot contract it to a point in the torus. So, for example, here is, I just see the cycle. So I'll do it in the continuous torus. So, for example, just to practice it, this is a cycle, right? Because it starts here, goes here. This is identical to this because we identify top and bottom, and then it goes here, and this is identical to this. And this, you see that it wraps around, actually in both dimensions here. And this cycle, we can look at some other cycle. So this one is trivial. This is not non-trivial because it doesn't wrap around. It's okay. And in fact, the only thing we will want to use about cycles that wrap around is that their projection on at least one coordinate is full. This is not an if and only if, but it goes in one direction. If a cycle wraps around, then this implies that a projection on some coordinate, maybe on more than one coordinate, is full. Okay, so this is something that we'll use. And then the final definition is what is called a spine. So a spine will be, but again, we'll have three of them. So I'll define a vertex spine. Vertex spine. So this will apply to the discrete cases, to any two of the graphs. So this will be a set of vertices that intersects, so intersecting each non-trivial cycle. And similarly, we will have an edge spine. So as you can guess, this will be a set of edges intersecting each non-trivial cycle. So if we delete this set of edges, no non-trivial cycles remain, and same for the vertices here. And then we have a continuous spine, so maybe I'll just call it a spine. So that will be a surface. I mean, we are in dimension d. It will be a d-1 dimensional surface. So surface, and again, intersecting each non-trivial cycle.
So I have a question. Is the horizontal line, is it non-trivial?
Yeah, so it's a good question. Let's look at it and try to. So the question is if, let's look at a horizontal line. Actually, a horizontal line is a cycle in itself, right? It's a non-trivial cycle. But it's not a spine, right? Because it does not intersect any other horizontal line, for example. So it doesn't intersect this one. But this.
The question was just whether it's non-trivial or not.
If this is a cycle or a. The question was.
A non-trivial cycle? Yes.
Yeah, sure. This is a non-trivial cycle.
So,
right. And it's
so maybe the definition should be non-contractible.
Yeah, it can be non-contractible cycle if you want. Yeah. So it's any cycles that you cannot contract to a point continuously on the. Yeah, so definitely a horizontal line is there. And these two things together are a spine, right? In this, because. Okay. We'll see. Now, what is the problems that we want? So, problem. I want to determine or estimate a mean possible size. Well, of course, size may be vertices, may be edges, or maybe d-1 dimensional volume, depending on. So that's why of spine. We want to know what it is. So how small can it be? Can such a spine be? Okay. Now, why would we want to look at such a thing? Maybe. Okay, so let's say something about motivation. So I'll mention three reasons. Each of them has some nice story behind it, but probably I'll not tell you much about it because it will take too much time. So unless you will really push me to do so, so I just kind of I'm saying more or less the buzzwords, but again on each of them I can tell you more. So the original one, so as I said, some versions of these problems have been considered before. The first one maybe is in a paper by Sachs, Morodnitsky, and Zosin. And their motivation came from integrality gaps in directed multi-commodity problems. And basically they show, specifically they looked at vertex spines in this second graph. I'll come to this again later. They show that every vertex spine here is big. You have to delete many vertices to destroy all cycles. But fractionally, whatever this means, I didn't even define it, but fractionally you don't have to delete much. You don't have to put too many weights to get a fractional spine if you define what a fractional spine means correctly, and therefore there is some large integrality gap, and it was somehow interesting for them. I promise that this will not make much sense, so I hope that convinced you. But okay. The second. Now here is the second one. It's there the story is even longer and is interesting, I think. So that's what is called a parallel repetition of the odd cycle game. And again, I don't want to talk too much about it, so maybe some of you heard something about it and maybe not, but it's somehow a nice, and this, the connection between this and one of these problems was pointed out by Feige and Kindler and Ryan O'Donnell. So these are all papers, I don't know. So this maybe is from, they are all from a few years ago, so it's maybe 05 or something. So again, let's leave it like that. The last one, I'll say something about it. So, so this is what they call foam. Maybe I didn't say here, but maybe let's just write it. That we have here we really have 5 different problems, right? Because we have 2 graphs, so yeah, that's right. So it's the first theorem I can prove. Well, I would have proved if I would have time. So we have 2 graphs, and for each of the graphs we have vertex spine and edge spine, and then we have the continuous one. So there are really 5 different problems, and all of them besides one are interesting. So somehow, okay. So foam. Let's look just to explain what this means. So this has to do with soap bubbles. Let's look at the best spine or smallest continuous spine for d equals 2. That's the only one that is known. So for d equals, well, for d smaller than 2, it's not interesting. For even for d equals 3, it's not known what the smallest is. But for d equals 2, this was done by Cho in '89. And it turns out that a shortest, so here it's just length, right? D minus 1 is 1, so you take here the midpoints of this, and this is the middle here, and then you take the point here that, so that every angle here is 120 degrees, and you do it symmetrically here. And this is, it turns out that this is the best spine. And if you repeat it, so you can repeat it periodically. Let's take another torus or square, another one, and just draw this same spine in each of them. So maybe it looks like this. Here it looks like this. And here it's like this. So you see that what you get in the middle, I mean, in this picture, and if I would do it periodically, we would get it everywhere. You get this bounded body, and it is bounded exactly because this thing is a spine. So if it wouldn't have been a spine, if there would be a cycle that is not blocked, then somehow this thing would not be bounded. We would be able to go to infinity without crossing any boundary. But this thing will be a tile, and the surface area, the length of the perimeter in this case, of the tile is exactly twice the length of the spine, okay? Because somehow every part of the spine is counted once here and once here. So, and this is something that tiles, because of the periodicity, it tiles the plane with respect to the usual lattice. And if the spine is small, it is something that tiles the plane, which has a small surface area, okay? Or here, a small perimeter, but in higher dimension, it will be a small surface area. And why foam? Because soap bubbles, it is believed that what they, or the physical model is that what they try to optimize is the surface area subject to all the constraints that they have to satisfy in the specific scenario. So here, if we think that we blow a soap bubble in the middle of every lattice point, and they all have to be the same, so it will be some periodic tiling, they will fill the plane, but because they try to minimize the surface area, they want to find the tile that tiles the plane with respect to this lattice and has the smallest possible surface area, or perimeter in this case. In higher dimension, it will be d minus 1 dimensional thing. And we want to understand how it is, and in particular, you see, in big dimension, so one way to tile is just to take a cube, to tile by cubes, boxes, and then the surface area will be d, 2D, right? But I'm not be interested in constant factors, so it will behave like d. Now, on the other hand, if we tile, then the volume of each tile is 1. So by the usual isoperimetric inequality, if we would even forget that this is tiling, if we have in d-dimensional Euclidean space any body whose volume is 1, then the surface area is at least square root d times some constant. So you can compute what is the surface area of a sphere. And therefore, the smallest possible surface area of something that tiles the space with respect to the usual lattice is something between d and square root d, and we want to know how it behaves. So can it really look like a ball in terms of surface area and still tile the space with respect to the usual lattice? Seems it cannot be really like a ball, but we want to understand it. Okay, so this is about motivation, and let me tell you something about what is known previously and what I want to show you today. So as we said, we have these 5 problems. Now, one of them is trivial, so this one is easy. Smallest edge spine in a CMD1 is of a size exactly 1 over m fraction of all edges. Namely, we have this torus here. So what we can do is we just cut these edges and we cut these edges. And what's good about this is that from every horizontal and every vertical non-trivial cycle, we cut exactly one of the edges. Well, we have to cut at least one edge from each of them, and we cut exactly one. And you can see, well, you can't see, but basically you can see that this is a spine, that every, okay. And it's obvious why it is the smallest possible, right? Because the whole torus here is just the edge disjoint union of those non-trivial cycles that look pretty trivial anyway, namely the horizontals, the verticals, the ones in each. So in each of them we have to delete at least one edge, and if we manage to delete in each of them exactly one edge, then of course that's the smallest. Okay, that's simple. Now here is one that that also is known precisely, but that's already a result. So it was so this will be the vertex spine in CMD infinity. So there also, the best spine is kind of the natural one that you can think about. You just cut the boundaries. So that's a result by Bolubash and also Kindler and Lieder, and also Ryan, also a few years ago. So they proved that the smallest vertex spine in this CMD infinity is of size, here we know exactly what it is, so it is of size exactly m to the d minus m minus 1 to the d, namely all vertices with a 0 coordinate. So you see this is this number, right? Because the total number of vertices is m to the d, and the ones which you do not have a 0 coordinate is m minus 1 to the d. And again, so this says that we kind of take maybe the most natural vertex spine, all the ones that are here, right? This and this. So that's the best that we can do, and as I said, that's already a proof. So they make some efforts. Actually, there is a remark here. So there is a very short proof, nice proof. But, this is something we observed with Ohad Feldheim, who is a student in Tel Aviv, that this, so I'll write, there are these, I'll write one line. There are these one-line proofs, but usually the trouble is that this one-line proofs, if you want to show the one line, you need a few pages of preparations before the one line. So I won't really show you, but really it's somehow, in some sense, it's a one-line proof, and it's even, which even gives a, which also gives all cases of equality. Cases of equality, and it uses something that maybe in retrospect is not so surprising. So using the Brun-Minkowski inequality, inequality, which says that for bodies in the d-dimensional space, if we look at the volume of the sum of two bodies, Minkowski sum, it's at least the volume of A to the 1 over d plus the volume of B to the 1 over d. And somehow there is a natural way to represent these things as we really replace every vertex of the graph by a small box that represents this vertex. And okay, and we say this one line, but I'm not going to say it. But yeah, there is this short proof. Okay, now so far, so these two results, one is trivial, the other is this. It's the very natural. So the smallest spine is what you think the smallest spine is, and how would you cut? You cut in each dimension, and that's it. Now the three others are all different. So they are all somewhat surprisingly small, and they are surprising in two respects. So one respect is they are smaller than maybe what we would expect, namely they are not what we get from the natural one. And also, in all these three cases, we don't see the spine. So there will be some proofs that they exist and that they are small, but the proofs are not explicit. So we don't see them. And it's in all these cases. Okay, so let's mention those. So maybe the first one is, again, in the paper by these guys, BKLO. So they say that smallest vertex spine in CMD1, so that was the one for which the edge spine was easy. If we want vertex spine is of size, well, now we don't know exactly, but at most some constant, d raised to the power log base 2 of 3/2 over m. So this will be fraction of all vertices. Okay. So always we need to take at least a 1 over m fraction of the vertices or edges in all these spines because of looking, let's say it's a horizontal non-trivial cycles. But they say, and kind of the obvious thing to do, which is what happened in the other two spines, is to take it in every dimension separately, and then we would get a fraction d over m. But this gives something like d to the 0.6 maybe over m. So it is somewhat smaller than what we expect. And as I say, we don't really see it from the proof, but there is a spine that is smaller. Now the next one, so as I said, so we still have.
I understand exactly what the big O means. So this is as D and M are both going to
yeah, so big O just means absolute constant independent of anything, like 5.5, I don't know. So not a function of M and not a function of D. Right? So, yeah, and actually.
That's interesting because you always have 1 over M, right?
Yeah. So you mean, right, yeah. So you want some.
One less dimension.
Yeah. But actually, since you ask it, I think that specifically, this will come later, specifically in their bound, actually, the constant is 1. So it could be, yeah. But later, I'm going to have all kinds of constants. So, and I'll not care about absolute constants. So whenever I write O, it's absolute constant. Okay, now here is so this something done by Randraz. So again, he formulated it for the parallel repetition problem, but it's equivalent to what I'll say now. This somehow was surprising, and this says it's the smallest edge spine in CM D. Infinity is of size, and again, we want as a fraction at most, and here definitely there is a constant, but it's again an absolute, just an absolute constant. And instead of, so we said that kind of the trivial upper bound will be d over m if we cut in all dimensions, but actually it gets square root d over m fraction of all h's. So again, it's small. And again, we don't, from the proof, we don't really see it. And finally, that will be the last one in the previous results. So that will be, the last one that was left is a continuous spine. And so that's really, as we said, it's the minimum surface area of a body that tiles the space with respect to the usual lattice. So that was a recent paper by Kindler. Well, it's the same. I mentioned them, O'Donnell, and now Rao and Witterzone. That's also maybe from last year. And they proved that the smallest continuous spine is of area at most, again, some absolute constant, square root d. So really it behaves like the surface up to a constant, like the surface area of a ball, not like the surface area of a cube. Right? So it's kind of very small. And okay, so this is what's known and what is new. So something I want to show you. This is something we proved with Boaz Klartak from Tel Aviv. So this one, actually, it can be much smaller. So this will be one result. And I'll tell you something about it. So this will be the smallest, again, vertex spine in CMD1 is of size at most, so then there is some absolute constant, and here instead of this d to the 0.6, it will be only log d. It will be really small, and again, fraction of all vertices. But maybe what's more interesting, so I'll tell you something about this, but basically we get, so each of these three results that give surprisingly small spines that we don't see is, each of the proofs is very different from the other two. And what we have is one approach that gives all of them. So basically.
So look at the square root d and
how tight is it?
Tight?
So up to a logarithmic term, this one is known to be tight. And, but there is some logarithmic terms that is not clear. This one is tight, yeah, because of the isoperimetric. So this one is tight up to a constant factor. That one is tight up to a logarithmic term. This one, I guess, is tight up to a logarithmic term because 1 over m is a trivial. But yeah, it's not clear, actually, if the logarithm has to be here.
It's not more than isoperimetric.
No. You mean if you can get in one of in this one something from an isoperimetric, no, it's yeah, it's from some other, right? Yeah, because somehow.
So 1 on m, that's the best lower bound.
Yeah, specifically for this one, it's 1.5 over m, if you want to. So somehow in dimension 2 it is known exactly, and in dimension 2 it's 1.5 over m, and whatever you have for some dimension, it is monotone because you can cut, like in 3 dimension you can look at the layers and in each one. But yeah, so it's, I don't know. Okay, but what I want to tell you is that this is plus same approach. Same approach gives other two small spines as well. Right, so it will give an alternative proof of this result of Raz and an alternative proof of this. Okay, and they will be very simple, all of them. So basically, now what is this approach? So general steps of proof of each of them, 2 steps only. So there will be step A and step B. So step A will be find or prove existence of a subgraph or body. So it depends if we are talking, if we are in the discrete case or in this continuous case. So we would want to prove that there is some subgraph or some body with no in the torus, right? With no, okay, right, in torus, with no non-trivial cycle, no non-trivial cycle, a small boundary, whatever small and whatever boundary means, so vertex boundary or edge boundary or continuous boundary, and how do we prove it, this existence? So this will be using an appropriate isoperimetric inequality. So I'll show you one of them, but in another case, so in the continuous case, it will be actually the simplest. In the continuous case, it will just be what's known as Chigger's inequality. So it's a known inequality. You kind of substitute in it, and you will get this existence. And then the spine. So this means that we are somewhere in the torus, and we get some body inside it, and it has a small boundary. This is the boundary. And it doesn't contain any non-trivial cycle, but it's still, there is no spine here, right? So it's one. So this will be step B, which will be simple. So I'll show you step B. Is that the spine is obtained by pieces of random shifts of maybe pieces of boundaries of random shifts of this subgraph or body. Okay. So again, this does not. So this will become clear soon. But this is basically how the proof goes. And I want to show you. Just have enough time to show you one of them. So as I said, they are all essentially the same. So I want to describe one of the proofs, and maybe the nicest will be to try to describe this one, because there indeed it's a new estimate. But as I said, basically all of them are the same. So let's see one example. So I want some isoperimetric inequality. Now, if I talk about this vertex spine in CMD1, then I need some vertex isoperimetric inequalities. There are all kinds of known inequalities. This will be something that is kind of simpler. So it's more or less the simplest. So here is an isoperimetric inequality for graphs. It is general. It talks about graphs in general. It's kind of independent of what I talked about. So even if you lost me or you've not been listening, you don't have to, but you can listen to this again. So this will be a lemma. It's a general thing about graphs. So all these things are similar to the kind of inequalities that you deal with when you talk about expanders, about the ratio between the so-called isoperimetric constant or Chigger constant and the eigenvalues. But this will be a simpler one. So this will be a discrete vertex isoperimetric inequality with Dirichlet boundary condition, if you want to give it a long name. But let me not write it. So here it is. If G is a general graph, U, a subset of V, non-empty, which is sometimes called boundary. Okay, it's good to think about it as a boundary because indeed in our example it will be the boundary of the torus maybe. And we define C to be the minimum or the infimum when it's compound. It's finite. So the minimum over all W, which are subsets of V minus U. So we take sets that do not touch the boundary. And what we look is at the number of vertices. I'll define it. So NW minus W, these are all the neighbors of vertices in W, but which lie outside W. And we divide by W, okay, where, as I said, N of W is a set of all neighbors, X in V, there is Y in W, so that XY is an edge, right? So if my set here is W, then the neighborhood are all the ones that are connected to W. So we want to know how small can the boundary of a set be if this set does not touch the boundary U as a fraction of the original set W. And we want to bound it by something. So if this is C, and if F is some function from V to the real numbers, the non-negative real numbers, let's say, okay, and F on the boundary, on U, it is identically 0, so it is 0 on the boundary, then this C is at most some expression. So let me write. So it will be the sum of F, I don't know, U over all U in V. And here it will be the sum, again, over all U in V of the maximum over all V in N U union U. So we take all the neighbors of U and U itself, and we take FV minus FU. We maximize over all these V's. This is always non-negative, this thing, because in this set I have U itself, so F of U minus F of U is 0, and we can get only something bigger. And the claim is that C is at most this thing. Now, why? So this is some isoperimetric inequality. It tells us something about it bounds this C in terms of some function. Why is it good for us? Because if we can find a function for the case that we care about, for which this thing is small, then it will prove the existence of a body or a subgraph with small boundary. Okay, so this is what, and this is not surprising, the expression here. As I said, the proof of this is not difficult. I'll not show it, but it's really not difficult. This is not surprising because you see, if the function f is a 0-1 function, a characteristic function of a set, then what is written here is exactly the boundary, because you see, so then you will get, well, here, again, if f is a characteristic function of some set W, here you get the volume or the size of W, because you get 1 for each vertex of W. And here you get 1 if and only if this U is a vertex on which the value is 0, but it's a neighbor of someone in which the value was 1. So it's in the boundary. So then this is, namely, if I would have known to choose the best f, then I could have got an equality here. But because it will be, the f will be a characteristic function of the w that gives us the minimum. But normally we don't know to do that, and the ability to choose a more continuous f enables us to get some bound. Okay? So as I said, proving this is not difficult. Let's leave it. And but the corollary would be will be that in CM, so we are in this step A, right? So I want in CMD1 to get a subgraph which does not contain non-trivial cycles and have a small vertex boundary. So the claim is that in CMD1, there is a W set of vertices, containing no non-trivial cycle, and n of W, the boundary, the set of vertices outside W that have neighbors in W divided by W, is small, is at most maybe 2 or 3 times a log D over M. Okay? And how do we prove this? So we just want to use this previous thing in a graph, in the graph G, which is this CMD1. Well, maybe. It will be more convenient. Not so convenient to write convenient. So it's convenient to consider a let's say C2M D1 on the set of vertices. Just will be easier to write down things. I want to put it so that the center is at 0. So it will be minus MM to the D on this set of vertices. Okay, M and minus M are identical, so I wrote it like this. So this will be the set of vertices. We'll define the boundary, boundary U will be all vertices which are in the boundary with a coordinate plus or minus M. Okay, namely, I have this torus, and I want to. So it's a graph, right? It's this graph that we considered, and I want to define. So that's a graph, and I want to apply to it this theorem. So I define as a boundary all this thing here. Okay. And now if I'll get here, so W is a set of vertices that is contained in V, the set of vertices, minus the boundary, without the green part. If we are without the green part, then definitely W will not contain a non-trivial cycle, because the projection on each coordinate will not be full, because we are missing the boundary here, right? So this will be, okay. So we just need to define some F here that will be 0 on the green part, and so that this ratio will be small, and then this statement will tell us that there is a W with small boundary, and again, W does not contain non-trivial cycles because it doesn't touch the boundaries of this torus.
So if you take W to be a smaller box, then
I could, but then I'll be in trouble because these things do not scale. So, so then the ratio will be very big somehow. Yeah. Normally, if you want the ratio to be small, you want to take big things, relatively big things, right? Because volume grows faster than surface area or something. Okay, so right, but so I'll just tell you what is this f. So define. Anyway, I'm not going through the precise computation, but it's not difficult. So define f of this x1, x2 up to xd. This is a typical vertex of the torus. So this will be the product of phi of xi. I goes from 1 to d. It's a product over the coordinates. And the function phi, yeah, I want to say something on step b. And I want to finish on time. So it turns out that a good phi of x will be 0. Well, it has to be 0. If x is plus or minus m, that's the boundary. And otherwise, it can be 1 over d times 1 plus 2 log d over m raised to the power m minus x. In any other case, x less than m. And then we somehow do the computation here. And it's not difficult to see that the ratio will be only log d over m. Basically, you see, well, you have to worry about the zeros. But if you forget the zeros, so somehow for every vertex u here, there is some fu here, and then there is a term here. If the term here is only 2 log d over m or something times the term here, then we are fine, because we sum over all of them. And this is basically what happens, because if we are a neighbor means that we change one coordinate, and the one coordinate exactly corresponds to multiplying it by 1 plus 2 log d over m. So the difference between them would be log d over m, and you have to look at it for a few minutes and convince yourself that that's the case, but it is correct. Okay, so we now plug in star, write star here, and get result. Right? Because an upper bound for C is exactly the existence of W with a small boundary here.
So is it already somehow non-constructive, or can you give us a clue?
No, yeah,
W looks
actually
like?
this part is not the bad part. The non-constructive part is really part B, and the trouble with part B also is that we have only 3-4 minutes for it. But
can you
but
sort of give us some clue what the resulting W looks like?
Yeah, so actually from the proof of this, the resulting W is always a level set.
Okay.
It's a level set of this function. So, but and in fact, so you know, you more or less know how it looks.
Yeah.
It's W. Okay. But the trouble is now with the random shifts. So this is the part that I want to try to say something about it. So B, we have this W, and now I want to get the spine. Let me try to show you quickly what is spine. So take an infinite sequence, x1, x2. Well, you will stop at some point, but this is in ZMD random. So each of them is random, independent element of ZMD, just point in the torus. Now we have the W from before. Define, put Wi will be xi plus W. Everything is in the torus. So I'll write here modem in each coordinate. So we take a random shift of this. This graph of the torus is vertex transitive. If W didn't contain a non-trivial cycle, none of these will contain non-trivial cycle. Now we define this Si will be the boundary of Wi minus everything that we saw before, the union over all j less than I of Wj union NWj. And then the spine will be just the union of all these Si's. I mean, I wrote it here as an infinite sequence, but of course, after finitely many xi's with probability 1, this covers all the torus, so we can stop there. So really, in a picture, what this looks, so we have this torus here, and then we have this body, maybe, and we took the boundary. And then we took a random shift of it, and we took the boundary of it that lies outside. Yeah, so is it? And then you take another random shift, and so on. And so some shifts can be modulo the torus, but I just... and then the claim is that this is a spine. That's easy to see. So no non-trivial cycle can be contained in one of these guys. And because of this, you can convince yourself that, so I just write that easy, because there is one nice point that I want to stress. So easy is that S is a spine. And now here is a crucial fact, fix X in the torus, in the MD. Now, let I be smallest the first time such that X belongs to Wi union N of Wi. So we have some point here. It's here. You see, so far it has not been covered. But now, in some shift, it's going to be covered. And then the crucial fact that is kind of trivial, but you have to stare at it for 30 seconds. You don't have more. So X is equal to Xi plus W, right? Because these are the points of Wi. And W in W union NW is uniform random in W union N of W. Namely, by the time this point will be covered by some shift of this, it can be covered by any point of this, and it's equally likely to be covered by any point. And this is obvious, right? Because for every point, if you want it to be covered by this, then the shift has to be exactly this. If you want it to be covered by this, the shift has to be... So there is exactly one way in which it can be covered by every point. And because of this, the probability that this point will lie in the boundary once it is covered is exactly the ratio between the boundary and the... Right? So therefore, the probability that X belongs to Si, which will therefore be part of the spine S, is exactly NW minus W divided by W plus NW, this thing, which is at most this log D over M. Okay. So each point, when it is covered, it has only a small probability to lie in the spine. And now just by linearity of expectation, expected size of spine is the total number of vertices times this O log D over M, and that's what we wanted. Right? And so this is this case. As I said, the edge version, so you have to use some edge isoperimetric inequality for graphs, and then you basically repeat the same thing. For the continuous one, the isoperimetric inequality is Chigger's inequality. You just write it down. There it's easier, actually, and the same for the edge isoperimetric inequality, because there it comes from eigenvectors and eigenvalues of some Laplacian operator, and there you don't have to be clever in inventing your function f. It's just the best eigenvector, so you know what it is. For the continuous one, for example, it will be the product of signs. So you just write it down, you do the computation, you get... let me just write two problems. Maybe I mentioned both. And then that will be the end. So two things that look interesting. One is that is the log D needed in this CMD one, in kind of the proofs that I sketched. So maybe it's a constant 1 over m. It's not clear. Yeah, I don't know.
Is the log type in step A?
Is the log D what?
In step A, or what is the log
Yeah, so if we do it in this way with a function that is a product of over the coordinates, then the log is tight. But I don't know. Yeah. Yeah. But I don't know in general. So this is. I mean, yeah. Otherwise, if you don't restrict on this function, it's the same question really, because if you delete the spine, then the thing that's left is a set whose boundary is just the spine. Right. So then it's the same question. Okay. But, so this is one, and then the second, which looks interesting, is to see how any of these spines how they look like. So, and the real non-constructive part is this random shifts. Somehow you don't have control. So.
But it's not really non-constructive in the algorithmic sense.
Yeah, not
you can
really.
Just de-randomize it, isn't it?
I can de-randomize if you think about m to the d as polynomial. If the size of my graph is polynomial, I can. Right. But what I really want, let's say, is a continuous one. So the continuous one is a pretty strange body, right? So you have a tile that tiles a space with respect to the usual lattice, and its surface area behaves like that of a ball. How does it look? I have no idea how it looks. It's kind of consists of pieces of things. I don't know. Yeah, it's yeah. So it will be nice to. Yeah, I don't know. Okay, so we are almost in time, and thanks for your patience. Yeah.